need to share with you that rare in my role as a non-traditional and high performance builder, would you ever hear me counsel to use less insulation or to consider reducing the R value in a particular building. By the end of this winter, Evolve will have completed nearly a dozen custom passive house quality homes, which, as this audience might know, requires the nth degree in insulation, thermal bridge attenuation, air tightness, among other considerations. So Evolve is built for producing hyper-performing homes. Now, high-efficiency homes, especially for the general consumer audience, and too for production builders, are often sold on the basis of how quickly these efficiency details are recovered in foregone energy costs. The closet statistician in me loves to compare numbers and scenarios, and this project offered Patrick and I the opportunity to assess, were there times where anecdotal experience or experiential knowledge might actually have led us unnecessarily to spend money on poor payback items? Are there situations where energy efficiency details might actually lead to a negative return? i.e., are there opportunities where, or potential for insulation to lead, in fact, to a lower ROI? I also need to note that this talk will speak about operating efficiency versus construction cost. It does not give consideration to embodied energy or embodied carbon, which, while a critical climate consideration, was neither the scope granted to us by our client, nor, as a result, the focus of this talk. What we did have is this particular site. And Patrick and I are going to use one project and two different envelope examples that surprised us in terms of their payback. Our project, with Evolve as the builder and cost modeler, and Patrick as the energy modeler and mechanical system designer, was a new family residence replacing an earlier structure in a mature neighborhood with a less than perfect 45-degree street frontage relative to ideal solar south. The owner presented us with several clear deliverables: a manageable but very firm budget, a desire to adapt a plan based heavily on a family member's own home. It also had to be very thermally comfortable, I'll even say quite warm. The homeowners, however, on the flip side, gave us relief from Evolve's common environmentally or more natural material use if those might be in conflict with other deliverables, in particular budget. They were seeking unpretentious detailing and finish materials, and because the homeowner is a representative for commercial PV products, those too were to be integrated into the design. And ultimately, the home was to be net zero.
So the term net zero gets thrown around a lot these days. But without a common definition, how do we even know what we're talking about? Net zero can mean different things to different people. It can mean net zero energy on a site basis or on a source basis, or it could even mean net zero carbon emissions. As Ben already mentioned, we're not talking about net zero carbon emissions, but we do want to give a definition for the project that we worked on here. And that's net zero energy on an annualized basis at the site. So that's at the meter. Ultimately, that's what our clients were aiming for. So this also happens to be similar to ASHRAE's definition of what net zero energy is. And that is a building which on an annual basis uses no more energy from the grid than is provided by on-site renewable resources. This also happens to be similar to the Canadian Home Builders Association definition for net zero homes. So there are some project-specific factors that we have to talk about here. When we talk about net zero energy, we look at both the demand side for the house as well as the production side in terms of on-site renewable energy. But it's the energy demand side that I'm really interested in. So we have, of course, our space conditioning demand for the house. That is your heating, air conditioning, dehumidification. We also have domestic hot water. Then there are the lighting and appliance loads as well as plug loads. This is probably something that most of you are already familiar with. But the thing unique to this project was that our clients asked us to include the electric vehicle charging for their definition of net zero into this project. So this definitely presented us with a challenge. As you can imagine, plugging in your electric car, if you have one, is actually quite a large demand in terms of annual energy use. It just so happens that in this case, our clients actually use their electric vehicle for approximately 15,000 kilometers over the course of the year, which, as you can imagine, would have a definite impact on how much solar PV you would need to offset that. But then again, who wouldn't want to be able to drive their car on sunshine? So here we have a problem, and we need to come up with creative solutions for how to achieve our goal. So we look to the wily disruptor-in-chief, Elon Musk, for some guidance. What Elon does is he uses first principles thinking in order to reduce the different components of a potential product down to their fundamental truths. That is, what is the physics behind it, and what are the material costs that go into making that product. In leveraging this type of thinking, we looked at our energy demand more closely. What we quickly realized was that the domestic hot water system was already decided that it would be a high-efficient electric system. That was a foregone conclusion. The appliances would also be highly efficient Energy Star appliances, pretty typical for a net zero or a passive house. Lighting would be all LEDs, so this was all understood. In terms of plug loads and electric vehicle charging, we did have some historic data from the clients from their old house, and with the knowledge that these factors wouldn't change too much going to the new house, we decided to basically consider these fixed demand in terms of energy consumption for the house. That really only left space conditioning and the rooftop solar sides of the equation to play with. So you can think of it as a giant seesaw. If you adjust one, it's going to affect the balance of the other. So in terms of the space conditioning demand, we looked at both mechanical systems and the building envelope. In this case, unfortunately tonight, we don't have enough time to get into the details of the mechanical system selection process, but we do talk about the envelope a lot. So we have to acknowledge that diminishing returns on energy savings by adding more insulation is a hard rule by physics. That's basically one of those laws that you can't change. We also understood there were construction cost implications for building different wall assemblies and roof assemblies and the like. On the solar generation side of things, we knew that we had a given site that was suboptimal in terms of orientation. We had a set design for the roof and what the house would look like. And then we also had a predetermined area, roof area. Add into that a little bit of shading from a large maple on the street, and we kind of were starting to realize what the constraints would be. We then employed energy modeling as our optimization tool in order to make decisions. So a lot of us energy nerds really like to talk about things such as diminishing returns on increasing insulation, but it isn't until you actually graph something like that that it really starts to hit home. In this example, this was generated from data for this project specifically, but you can see that if you go from an R5 wall assembly, which of course that's not going to get you to net zero, that's also not the point. If you add R5 worth of insulation to that assembly to achieve R10, you're dropping the annual space conditioning demand by 43%, which is substantial. Why wouldn't you go to the next level? Well, what we quickly see is that you end up with diminishing returns on insulation. That same additional R5 worth of insulation added to an R35 assembly to get you to R40 is only actually going to get you a 5% reduction in your annual space conditioning demand. So with all of this information kind of in the back of our heads, we decided to undertake an analysis of what is the ultimate constraint for the project, and that is how much energy can be produced by a rooftop PV system. In this case, we determined that given the space, we could have 23 kilowatts potentially on the roof of the house and the garage. We then mapped that out in terms of dollars, considering approximately $2 per watt for installed PV. We also looked at what 15 kilowatt solar PV would result in and kind of set that as our aspirational target. All of these obviously have kind of the balance in terms of how much energy your house is allowed to consume to hit these numbers. For the purple bar on the graph here, that is basically using Evolve's standard high-performing building envelope assemblies and applying that to this predetermined house design in terms of floor layout and configuration. And so we determined what the annual space conditioning and overall energy consumption for the building along with EV charging was, and how much it would cost to offset that with rooftop PV. Now, this is where it kind of gets interesting, because in addition to this exercise, we went through an optimization exercise and looked at different assembly types, different insulation R values, and started to integrate cost analysis into this using estimates provided by Ben.
So with Passive House in particular, and to a lesser degree too with net zero, we professionals invest hundreds, sometimes thousands of dollars per unit in incredibly careful and detailed energy models. We assess energy demand down to the plug loads. We examine thermal bridges of every stud member. We use powerful tools like HOT 2000, or more commonly now for Passive House, WUFI and PHPP. And then we verify our work down to the second decimal when testing airtightness. This is all ideal. In short, though, we're putting a great deal of effort and emphasis on energy modeling. And after that, I asked the question, why is it too commonly allowed that you request of your builder, such as us, to use the WAG method of cost estimating? Anybody familiar with WAG? Wild ass guess? Of course, we don't label it that. In the industry, we'll call it Class D, or ballpark estimate. But that's effectively what you're asking for against these highly detailed energy models, and the two are incongruent. If you are following that path, what it means is that with certainty you're leaving your clients money on the table unnecessarily. For this project, as Patrick said, we each selected a variety of different building components around which we not only modeled that energy implication of each substitution, but we also carefully modeled the construction cost implication of each one of those as well. And for this talk, we're going to focus on above-grade wall assembly and the window package. Patrick assessed the energy impact, and we calculated the construction cost, all other things being equal, between two different wall assemblies. Both wall assemblies had in common the same structural service wall, a 2x6 frame wall, looks pretty common, to which we started with Evolve's standard Passive House wall assembly. That consists of a series of truss joists acting as deep furring, sandwiched by a sheet of plywood into which dense packed cellulose is poured effectively from above. And this is a basic wall assembly that will be familiar to those of you who are Passive House practitioners in the audience. We then took that same assembly, starting with the same 2x6 frame wall, common to both examples, and substituted the outboard truss joists and cellulose for a simple 6 inches of EPS insulation. For the window package, we determined the cost implications, and Patrick determined the differential energy gains and losses between Evolve's standard triple glazed window product and a downgrade to double glaze. It even hurts me just to say that, especially out loud. And I know Alec and Sarah, that I recognize that this is going to earn me a special place in Passive House hell for even suggesting something other than triple glaze, much less your product. But nonetheless, when it was a net zero home that we were examining, we had to take a look at, or we decided to take a look at all options. So Patrick had already discussed that our benchmark, which is the purple graph on the left, at roughly $36,000, that's the equivalent cost in photovoltaics that was necessary for the homeowner to purchase in addition to our, or Evolve's benchmark or base products in order to bring that house to net zero. What did we discover when we examined these two different wall assemblies or elements of the wall by examining those, both the truss joist versus EPS and the triple pane versus double pane, is that first, I'll start with the wall assembly. As one might expect, the EPS wall assembly required a greater investment in photovoltaics. You can see that bar is just slightly taller. The blue bar, second from the left, is slightly taller than the purple bar, which is our benchmark. What that represents is about $600 in photovoltaics necessary to get to the end. I was integrating Yuri's sign of running out of time. We also, by substituting the lesser windows for the original triple pane, it had a greater effect on this particular house. About $1,800 more in PV would be required to offset that building performance. But thus, if either of these substitutions resulted in construction savings of at least that amount, $600 or $1,800 respectively, then the downgraded construction option is actually economically a better decision. So how did this work out? Well, in fact, the lesser wall system provided a cost savings of about $12,500, and the lesser windows was about $7,000. What were the decisions then that were made based on that? Well, of course, thankfully, not every client decision is going to be solely financial. While our clients did indeed opt for the substantive ROI improvement of the wall assembly choice, they opted to retain the triple glazed windows regardless of that incremental cost. And that's because one of the underlying project criteria was occupant comfort. Given the amount of glazing in the core public spaces and the intentions for furnishings, the ability to be comfortably seated near some of those windows in winter was more important than the construction cost. On all other matters, the client did decide to pick the better performance option, except for attic insulation, which too turned out to actually have a low ROI despite the nominal increase in construction cost. So one easy decision was, while it's not purpose of this talk, and was the selection of a then new to us combination HRV air source heat pump. Using this, the total mechanical system construction cost was actually lower than our benchmark price, and the energy performance was higher. So win-win on both sides.
So did we end up actually achieving our goals? I would argue that yes, we did, because we ended up with a house annual energy demand of approximately 9,250 kilowatt hours per year. Adding to that the EV charging, we got a total energy demand of 12,000 kilowatt hours per year. So that was able to be offset with a 15.5 kilowatt DC rooftop solar PV system for production of about 12,000 kilowatt hours per year. So we were able to almost hit our aspirational goal of 15 kilowatt rooftop PV, as well as offering the occupants a great deal of comfort in their home. And so basically, just to summarize the energy efficiency side of things, the performance was quite well. The clients have been in their home since October, so we're eagerly awaiting the full first year of data in order to see if they actually hit it on an operational basis, with, of course, the one major wild card in all of this being that occupant behavior can really impact things. 30 seconds.
And on the money side, by combining equal rigor to energy modeling and cost modeling of various building iterations, we assured that our clients received best value for their money. We saved roughly $20,000 in construction costs, we verified the soundness of other investment decisions, and ultimately, we reached the goals as Patrick described. We delivered less insulation and a better ROI. Thank you.